This is a demonstration of the XCS eiConsole from Pilotfish Technology. The first thing you see when you start the eiConsole is the File Management dialog. This displays a list of all the interfaces deployed on a remote EI platform server and in your local working directory. What I'll do is open up one of these interfaces to show you how they can be defined, modified, tested, and deployed. This table represents a route. A route is a directional transformation from any number of source systems, represented by each of these rows here on the left, to any number of target systems, represented by each of these rows here on the right. Each column in the table represents a separate stage in the processing of a transaction, with data moving through the table from left to right. We'll take each of the columns in turn. The first stage represents the source system. Here, you can enter metadata information describing the source system. This doesn't affect the behavior of the transformation, but it can be used for reporting, logging, auditing, and other management purposes. The next stage is the listener. Listeners are modular components that are responsible for bringing data into the EI platform. What we've configured here is a database listener that periodically executes a SQL query against a database and then generates transactions from the results returned. However, if I click this drop-down menu, you can see that we have a wide variety of other listener types available. Note that as I move through these options, the configuration panel behind the drop-down changes. Among the listener types we support, as I said, are database listeners, directory listeners that periodically poll a directory and generate transactions from the files within it, web service listeners, email listeners, FTP listeners that can connect to FTP servers using a number of different authentication mechanisms. We can expose HTML forums and produce transactions from submitted results, as well as receive raw HTTP posts directly. We can connect to the Java message service and through it systems such as IBM's MQ series. We can be invoked from within Java programs running on the same JVM or remotely through Java RMI. We can expose SOAP web services, again using a number of different configurations, and there are some more esoteric listener types available as well. I'll set this back to database before we continue. Once a transaction has been received by a listener, it can optionally be passed to any number of chained processor stages. Processors are modular components that perform high-level operations on the incoming data, such as decryption, decompression, character set conversion, validation, and so forth. For this particular route, no processors are required, so this table is blank. Once a transaction has been received by a listener and passed to any configured processor stages, the next step is the transformation. Here, the data is transformed from whatever physical format it was originally in into the canonical XML format that's being used in this particular route. In this case, that's Accord P&C, but it could conceivably be any other XML standard. The transformation itself is a two-stage process. The first stage takes the data from whatever non-XML format it was originally in and translates it into what we call intermediate XML. This isn't the canonical XML format yet, it's merely an XMLized version of the source format, which closely matches the structure of the source format. The second stage takes that intermediate XML file and applies an XSLT transformation to translate it into the canonical XML model. In this particular source, we're reading a fixed width file containing an auto claims record and translating it into an Accord P&C message. The tool that we use to define the layout of the fixed width files that we read is called the File Specification Editor. I'll show you that now. Here on the left, we have the layout of the files that we're reading, including all the record types. In this file, there's only one. If I actually click a record type, I can load in a preview file containing an example of that record that lets me see how the record will be parsed right here in the editor and verify that it was parsed successfully. So see here in the preview record structure, this is the contents of our sample file. And these handles let me click and drag to redefine field widths if I find a mistake or if the underlying record layout changes. And you notice if I click a field here on the left, the corresponding field is highlighted in the preview record structure. Now this file that we're reading has a very simple format. As I mentioned, it only has a single record type, but we can use what we call record controls to support arbitrarily complex file formats, including any amount of looping, nesting, repeating records, and so forth. We can also import record definitions from basically any way you have of specifying them, COBOL copybooks, Excel spreadsheets, and so forth. As I said though, that's just one stage of the transformation. The file specification editor defines how we transform that fixed width file into XML, but we still need to define how we transform that intermediate XML into the Accord PNC model. That's done using the XCS data mapper, which I'll show you now. The data mapper has a three-paned interface. The pane on the left represents the source format, the pane on the right represents the target format, and the pane in the middle represents the mapping. So if I expand the source tree here, you see this is the same record layout that was defined just a minute ago in the file specification editor, and here on the target side we have the full Accord PNC standard. And again, here in the middle is the mapping between them. I should note that this is actually a full-featured XSLT editor. We have full access to all of the XSLT structures and functions, and at any point in the mapping process I can drop down to the XSLT view and see the source code that underlies the mapping itself. This editor here is a full-featured XSLT editor. It has syntax highlighting, error highlighting, and code completion, and any changes that are made here in the graphical drag and drop view are immediately reflected in the XSLT view, and vice versa. The mapper is an extremely powerful tool that has many Accord-specific pieces of functionality. For instance, for any data element in the Accord standard, I can actually view the Accord documentation for that element right here in the mapper. And this documentation is searchable, editable, and so forth. The mapper is a very powerful tool, and it's covered in more detail in a separate demonstration. Now, once data has been transformed into the canonical XML format, it enters the router. The router is responsible for determining, based on the data within the transaction, which of the available target systems to send it to. For this route, we've configured a simple all targets routing rule that simply sends all transactions passing through it to both of the target systems. However, we have the ability to use XPath rules as well as custom Java modules to express arbitrarily complex logic, again, based on the data within the transaction, to pick which subset of the available target systems to send it to. Once a transaction has been routed to the appropriate target systems, the next step is the target transformation. This uses the same two-stage process that's used on the source side, except it runs in reverse. So the first stage uses XSLT to transform the data from the canonical XML model into an intermediate XML format, and the second stage takes that intermediate XML format and translates it into whatever physical, potentially non-XML format is required by the target system, such as a fixed width file, delimited file, PDF form, serialized Java object, and so forth. In this particular source, our target system accepts Accord messages directly, so neither of these transformation stages needs to be used. The final step, once data has been transformed into the format appropriate for each of the target systems, is to physically send it there. That's done in the transport stage. Before this happens, however, we can pass a transaction through any number of chain processor stages, just as we could on the source side. As I mentioned, processors perform high-level operations on the data, such as encryption, compression, character set conversion, and so forth. Again, in this example, no processors are required, so none are configured. The transport is a modular component, basically the mirror image of a listener, that's responsible for physically sending data to the target system. What we've configured here is a directory transport, but if I click this drop-down menu, you can see that we have the same wide variety of transport types available as we do listeners. Once you've developed an interface, the next step is to test it. To do this, I'll put the eiConsole into testing mode. From here, I can test any of the stages in the interface, either individually or all at once, including connectivity to the source system through the listeners, and connectivity to the target system through the transports. What I'll do is I'll start a test immediately after the listener in the fixed width file source that we saw earlier. To do this, I'll select the appropriate stage in the table diagram, click Start Test here to indicate that we want to begin the test at this stage, and I'll select that example file that we saw being loaded into the file specification editor. Note the arrows that have appeared on the diagram indicating which of the stages in the interface will be included in our test. When I click Execute Test, you'll see a series of green check marks move across the table indicating successful completion of each of those stages. The only exception will be the transport stages because these have been configured with transport locations that are not accessible from this workstation. I'll execute the test now. Now we can look at the output individually of each stage in the processing of this transaction. First though, let's look at the file that we supplied. As you can see, this is a fixed width file containing a single auto claims record. If we look at the output of the first stage of the source transformation, we can see that it's taken that fixed width file and translated it into an intermediate XML format. This isn't the canonical XML format yet. As you can see, it's a very flat structure that matches the structure of that original file, but it is in XML format. Now, if we look at the output of the second stage of the transformation, we can see that that XSLT style sheet has been applied to that intermediate XML file and produced an Accord P&C claim service message containing the data that was within that file. If we look at the output of the router, we see that it's unchanged, which is to be expected because the router never performs any data transformation. And now we can look at the output of our two target transformations. The first target transformation, as I mentioned earlier, is unused because the target system accepts Accord P&C messages directly. So if I look at the output here at the end of the transformation, we see it's in that same Accord P&C format that was produced by the source transformation. However, the second target system in this interface is an insert into a database. And so if we look at the output of the XSLT stage, we see that it's produced a SQL XML message. SQL XML is just a simple way of describing XML queries to be executed by the database transport, and what's represented here is simply an insert query against the claims target table. Now, because the database transport accepts those SQL XML messages directly, the second stage of the transformation that would normally be used to translate the intermediate XML file into some physical non-XML format is unused. And so if we look at the output here, it's that same SQL XML message. Finally, having developed and tested this interface, the next step is to deploy it. To do this, I'll go back to the file management dialog that we saw at the beginning of the demonstration. The eiConsole can connect to a remote EI platform server through a web services link. This allows us to perform a number of operations. First, we can commit any changes we've made directly to the remote server, even if the route we've changed is currently processing transactions. Second, we can update our local copy of all the routes to the latest versions deployed on the remote server, giving us easy access to changes that colleagues have made. We can also revert a single route that we've changed locally to the current version on the server. This is useful if, for instance, we've made local changes that we'd like to discard. Finally, we can lock and release routes on the server, allowing us to prevent other people from editing them while we're making critical changes. That concludes this demonstration of the XCS eiConsole.